So, ladies and gentlemen, we continue with René Henrion. So, please, the floor is yours.
Thank you very much. It is a great pleasure for me to give a talk at this conference dedicated to the memory of a great Hungarian mathematician and actually a pioneer of stochastic optimization, András Prékopa. And I have to say that my own research has been impacted very much by the work of András Prékopa, and I always enjoyed very much discussions with him, as at this conference you can see here 20 years ago, and appreciated very much his hints, which helped me a lot to proceed in my own research. But it was not only a direct impact, it was also an indirect impact via the students, PhD students of András Prékopa, and notably Tamás Szántai, who has unfortunately passed away recently, but also by István Deák. So in my talk, I want to discuss a bit chance constraints in the setting of optimal control, which is a rather new topic of research. And on the first slide, I would like to illustrate a bit that this topic is of much importance in real life. It is the problem of capacity maximizations for gas network owners. Okay, gas transport has recently become a highly political topic, but leaving this aside, the model for gas transport is as follows, at least in Germany. A gas network owner sells booking capacities to clients, and the clients can nominate loads for gas each day or each hour within these booking capacities. They buy these booking capacities, more capacity, the higher the price. And on the other hand, the network owner is obliged to serve, to make sure that the gas can be transported, which is nominated. And this is this possibility of gas transport is here shortly abbreviated by this set script T, and I'll come back to this in a moment. Now, clearly, the gas loads, the demands are random, and here you can see some statistical model of historical real-life data. These are different scenarios of daily gas consumptions around a mean pattern, and now the viewpoint of the gas network owner is, I will not try to satisfy all possible loads within the given booking capacities, because mostly the loads are concentrated in small areas within this booking interval. So I will be satisfied with a setting where I can satisfy the load maybe at a probability of 90%. And then if there are exceptional situations where this load can not be covered, there are operational means to regulate this, but this is outside the optimization problem. Now, let's say the gas network owner is satisfied with meeting the loads at a probability of 90%. Now he may discover that for the current booking capacities, he is able to satisfy the random loads even at 99%, much more than he would really require. That means he has some reserve to offer additional booking capacities to new clients, and keeping the level of 90%. And these new clients could be, for instance, owners of gas reservoirs, which do not behave in a stochastic way. They do optimization. You don't have historical data, you cannot model distributions out of that, so you don't know anything. And this takes us more to the setting of robust optimization. So on the one hand, we have historical clients with gas load Xi. It's a vector for all nodes in a network like this one of Germany. And on the other hand, we have new clients which could nominate arbitrarily within the given booking capacities. And now the optimization problem of the gas network owner is maximize the offer of additional, let's say, hourly booking capacities, which new clients could arbitrarily use for nomination without stochastic information. And this leads us to an optimization problem with chance constraints, as written down below. You want to serve the sum of loads of the historical clients plus, say, a new client like a gas reservoir owner for all possible nominations of the network owners. This is the robust part of the story, but the overall should be technically feasible with the possibility, with the probability of at least little p. So this is a mixture of a probabilistic and a robust constraint, and I'll come back to this in a moment. Now, I didn't tell you what I mean by this abstract set script T of feasible technical realizations. This models the gas transport, the physical gas transport, based on the so-called Euler equations, which are in terms of pressures and flows along the pipes of the gas networks. And the crucial constraint in all this is that the pressures have to satisfy a certain pressure limits. They have to stay between minimum and maximum pressure limits, but they become random because the load is random, and that is why you end up at such a probabilistic constraint. And here's just a short illustration of solutions for the vector of free capacities, which you have maximized. So this is what you can offer in addition to existing bookings to new clients, but it's a function of time. It depends on the hour during the day, how much you can offer. And here you see realizations of pressure scenarios, which are a sum of the stochastic scenarios plus the worst case possibilities imposed by this new client. And you can see here in this picture, most of them stay between these lower and upper limits, and maybe exceptionally a few of them violate them, which is coherent with the setting of chance constraints. Now, let me go more to the abstract setting of chance-constrained optimization problems. Let Xi be a finite-dimensional random vector, S-dimensional random vector. Then the classic setting means that you minimize some objective function, capital F, subject to such a chance constraints where you take the probability over a finite system of random inequalities, GI. And the decision vector X is supposed to be finite-dimensional too. This is the setting considered in the work by András in his monograph and in most part of subsequent works. Recently, a more general setting has attracted some interest, the so-called robust setting, which is an aggregation of probabilistic and robust. And this means that you allow here in this system of random inequalities an infinite number. So these inequalities are indexed by some little v, and little v is an element of some compact, I'm sorry, this should be, the d should be a v here, of some compact set, which gives some analogy to semi-infinite optimization. And the reason to do so is that, for instance, you are interested in time-continuous problems. So in András Prékopa's monograph, you have this, or in his work, together with Tomáš Szanto, you have this regulation of Lake Balaton, and so you want to keep the level of the water level within limits with high probabilities, but discrete in time, January, February, March, and so on and so on. But now imagine that you control a water reservoir, let's say for a day or 2 days, but you want to do it continuously in time. So for each time, this random inequality should be satisfied. And then this takes you to this setting. You could also think about this for all, which gives the taste of robust optimization, as in the gas problem I discussed before. That was the reason to call it robust constraints. Now, in principle, you could pick up this model for robust constraint also in the optimal control with, say, random partial differential equations. And then here you would now go from the finite dimensional decision space to an infinite dimensional decision space. I switch from X to U, as it is usual in control to call the decisions U's. And capital U is a Banach space, and G would be the control to state operator. So with the control U and the realization of the random vector Xi, you associate a state, let's say y, little y, and you evaluate the state, little y, at the position x, let's say a spatial position x in a compact domain. And you want to keep the state uniformly below some thresholds on that domain. There's one problem with this. This setting is fine as soon as the state is regular, let's say continuous and so on. But typically, states are just equivalence classes of measurable functions. So it has no meaning to evaluate a state. Often it has no meaning evaluating a state at a particular point. Because you can end up the same equivalence class by having a different value at that point. And then this makes it impossible to work with this robust setting in control problems. And the right way to overcome this is to go into a functional description of the constraint rather than having these point-wise evaluations depending on X. You directly consider the control to state operator G, and you say it has to fall into some subset capital K of the image space the state belongs to. For instance, all non-negative functions of L2 or H1 and so on. And in this way, you avoid this point-wise evaluation. It's a more abstract setting, but I think it's the right setting of chance constraint in control problems. Just to give an example, a simple control or a control problem subject to a very simple linear elliptic partial differential equation, which is Poisson's equation, so minus Laplacian equals some right-hand side, and the right-hand side is on the one hand a control U, which you decide on to, let's say, to minimize some cost function capital F of U, and in addition to the control you have some random source term little f, and this little f is supposed to be the sum of some expected source term f0 plus a linear combination of several base function capital little phi, where the coefficients are realizations of this random vector Xi. This corresponds to somehow what you are doing when applying the Kahun-Loew expansion in order to reduce a general stochastic process to a finitely parametrized one. So the random vector is still in finite dimensions, but we are in L2, which is Banach space. And now the state constraint we want to satisfy is the following. The state should be less than some threshold little alpha, almost everywhere on the domain, and with probability at least little p. Now to translate this into the abstract setting, we have a control to state operator from L2 times Rm into H10, this Sobolev space. That is PDE theory. So for each right-hand side here in L2, you get a unique solution of this PDE, which is in that space of certain measurable functions. This is our image space capital Y, and within this image space capital Y, we consider the convex set, or the convex set. It's not a cone because alpha is maybe not 0. It's a convex set that the states are less than alpha almost everywhere on the domain. And in this way, we can rewrite our concrete problem in the abstract setting below, which we introduced before. Now, it would be nice to get some knowledge about the solution of this problem. For instance, do there exist solutions to this problem, existence, or can we derive optimality conditions? And this is what we want to do next. We have the following results on general properties of chance-constrained control problems. We are in the setting introduced before. And we define this probability, which appears in the probabilistic constraint below. We define this part as the probability function phi assigning to the control the probability of keeping the state in the region K. And if this set K is weakly closed and the control to state operator is weakly sequentially continuous, then without any assumptions on the distribution of the random vector, you have that this probability function is upper semi-continuous, which is nice because the feasible set defined by the chance constraint is just an upper level set phi of u larger than p of some upper semi-continuous function, which means that M itself is weakly closed. Weakly sequentially closed. And now, a big reference to András Prékopa. If, moreover, this set capital K is convex and the control to state operator is linear, as in the case of our example, and psi, this is important, this is here where Prékopa comes into play, has a log concave density, for instance, Gaussian one, then the probability function is log concave, and you can rewrite this set M by taking logs on both sides, and this gives you a convex description. So M is a convex set, but here this description is not necessarily, the phi itself is not convex. It's a probability function. It's squeezed between 0 and 1, cannot be convex or concave, but passing to the log, you get a convex description of this set. So you are in the framework of convex sets. And of course, everybody here in the audience knows this is a famous theory developed by András Prékopa in the classical setting. We have reformulated it in this control setting, and it is no deep mathematical step to go there. It's a half a page of more or less evident manipulation, so there would be good reasons to call this Prékopa's theorem as well. But in those times, only finite dimensional decisions were of interest and only finitely many random inequalities of interest. And now it turns out how much impact these traditional or classical results have on more general classes with chance constraints. And if we go back to our little application problem, we see that we know that the control to state operator is actually continuous and linear, so it is weakly continuous. And this set K modeling the random state constraints is clearly convex and closed, hence it is weakly closed. And we have an optimal control problem with just one inequality constraint which defines a weakly sequentially closed subset of capital U, which is L2. excuse me. And now the classical existence theory for control problems tells us that, for instance, if the objective is coercive, convex, and lower semi-continuous, think about norm of u squared. And if the feasible set is non-empty, this is, of course, has to be guaranteed by choosing the right level of probability, then the whole problem is a convex optimization problem and has its solution. And if F is strictly convex, it has a unique solution. So existence is fine, but we would like to learn a bit more, for instance, about optimality conditions. And in order to do so, we recall that we have access to a convex description of the feasible set here. And this is what we are going to exploit in the following. We rewrite our optimal control problem by using this equivalent convex description, minus log phi plus logarithm of the level is smaller than 0. We assume that f is the objective is convex and continuously differentiable, but concerning little phi, it is in general not differentiable, even if you have perfect data like Gaussian distribution and very nice constraints G here. Still, phi could turn out to be non-differentiable, but it is Lipschitz under very mild conditions. But it's also not convex, it's just Lipschitz. So talking about constraint qualifications, optimality conditions, you would think about Clark's subdifferential. Now, first of all, using the convexity of this problem, we can, of course, formulate under Slater's constraint qualification necessary and sufficient optimality conditions by using the convex subdifferential of this convex function, which is minus log phi, plus non-negativity of the multiplier and complementarity conditions. The problem is that in order to reduce the subdifferential to something which is in terms of phi itself, we don't have access to kind of a chain rule for the convex subdifferential because the phi is not convex. But what we can do is we see, of course, the convex subdifferential for convex functions is the same as Clark's subdifferentials for convex functions, and Clark allows a chain rule. So you can break this Clark subdifferential down in terms of this formula here. And then you have a necessary and sufficient optimality conditions in explicit terms of the probability function, where here now occurs Clark's subdifferential. So it's an interesting phenomenon. The phi is not convex, and yet you can derive necessary and sufficient optimality conditions for this problem. And this is the hidden log concavity of the random vector behind, so it is Prékopa behind. Still, this is a nice formula, but, well, usually the derivative of the objectives is no problem, but how about the subdifferential of the probability function? This is a hard problem, and it turns out that we are able to find an exact formula and a fully explicit formula of this Clark subdifferential, which is amazing because usually when the function is not Clark regular, as is the case here, not Clark regular, then you just get typically upper estimates for the Clark subdifferential. But we were able to get an exact formula, and moreover, this exact formula involves quantities which you can explicitly calculate numerically. So it's ready for application. This right-hand side here is an integral. It's a multi-valued integral in the sense of Aumann. So the integrand here is set-valued. You take the closed convex hull of a certain set. So it's, the integral itself is a set consisting of all integrals over all measurable selections of this set-valued mapping. And integration is done over the unit sphere with respect to the uniform distribution. So you may wonder what is the reason for the unit sphere here. And this is very interesting. the fact that elliptically distributed random vectors can be decomposed into a random vector which is uniformly distributed on the sphere, and a one-dimensional random vector, and for instance in the Gaussian case it's the chi distribution. And this fact has been known for a very long time in statistics, but I think the first one who introduced this to the stochastic optimization community was István Deák. And we took this and found out that this is not only interesting for computational reasons, as was noticed by István 45 years ago. It's a strong variance reduction over crude Monte Carlo, which takes place by this spherical radial decomposition, but at the same time is very useful for sensitivity analysis of probability functions, as you can see here. It allows you to get differential and subdifferential information about the probability function. And under certain conditions, you can derive strict differentiability as well. I will not go into the details of how these items are calculated. This is illustrated in this, on this slide here. Rather, I want to show how it can be applied. So combining this exact formula for Clark's differential with our necessary and sufficient optimality conditions we have written down here, we get necessary and sufficient optimality conditions fully explicit in terms of the original data of the problem. And we applied it to a concrete problem, and we found a solution. A solution is in L2, so it's an L2 function. This is the red one, which we found by our numerical approach using, again, spherical radial decomposition. And alternatively, we applied a different approach from the literature, which was based on convex approximations. It turned out the optimal values of both solutions were pretty close, so one relative difference 10 to the minus 3. So which one is the right solution? Which one of the two is the right solution? And in order to figure this out, we applied this relation here. Actually, the inclusion here becomes an equation because this derivative turns out to be a single-valued object, a classical derivative, and which means at a solution, the derivative of the objective should be a non-negative multiple of the derivative of the probability function. And now we plot here at our solution the derivative of the probability function, which is an element of L2 as well. It looks basically the same as our solution because our objective was norm u squared. When you derive it, you get basically u. This is the derivative of the objective, and this is the derivative of the probabilistic function, of the probability function. Looks like 0. But it is not 0, it's just a matter of scaling. It's very small scaled. When you and the same picture here for the alternative solution. But when you multiply the derivative of the probability function by 60,000, you get this function here and here on that place. And if you find the right multiple, namely 82,000, then you recover exactly the derivative of the objective function, which is the optimality condition. And if you do the same with the other solution, you see it does not match. It does not match the derivative of the objective, and you can increase the multiplier, but it will never. You already can see here from the picture, it will grow, and it will never meet the blue function here. So it was an identifier of the right solution. And my final slide should convince you that all this is not only applicable to the simple Poisson's equation, but to general PDEs. As far as numerics are concerned, they can be nonlinear, as for instance in the gas network problem. But as far as theory is concerned, like convexity of the feasible set or Lipschitz continuity of the probability function, things become very difficult whenever the dependence of the control to state operator and the random variable is not convex. So linear is perfect, it runs very fast, and convex would be possible as well. But if it's non-convex, then one runs into technical troubles in verifying analytical properties of the probability function. That's all I wanted to say. Thank you for your attention. Köszönöm szépen.
Let me thank you again. This wonderful talk, René. Let me thank you this talk with this certificate about your attendance and with this gold medal of the Hungarian Academy. So thank you again.
Thanks very much. It's a great honor for me. Thank
Little setup. So the next talk will be delivered by Marco Campi. So the floor is yours, please.
Okay, so thank you very much. It's indeed a big honor for me to stand here today before you on this very special occasion, which is the workshop in memory of Professor András Prékopa, who I believe has been a giant in the field of stochastic optimization, and he has much influenced my own research, as I will try to sketch during my presentation. The title is the randomized alternative to chance constraints. So perhaps here we'll take a small departure from many other talks that have been presented and will be presented in this workshop. So let me start the very simple manner here. So this is the typical chance constraint that writes there is a function g of x and psi. X is the optimization variable, psi is the uncertainty variable, and we require that this function is less than or equal to 0, but not always. So this is enforced with the probability p, which is at least 1 minus alpha, and alpha is called the tolerance parameter. And we all know that even when g is a well-behaving function, say convex in x, the feasibility domain for this constraint turns out to be highly non-convex in general. And one of the fundamental results Professor Prékopa gave is to establish conditions under which the domain turns out, in fact, to be convex. You know, his celebrated results saying that if G is jointly convex in X and psi is having a log concave distribution is, you know, a masterpiece. And this has really opened an avenue for applying this kind of constraints in so many different fields. I had to say that my original background is not in stochastic optimization. I'm a control people. I come from the control community. And if I look back some 25 years or so, I mean, let's take 25 just to say a number. This kind of constraints were very popular, and they are even now. But, you know, let's go back to the time. So this is called an LMI. It's just a special case of Gx and psi less than or equal to 0. So it's called an LMI, a linear matrix inequality, because the L0 and Lj are matrices, square matrices, and the X sub j are the components of the optimization vector. So it's linear because the X sub j's appear linearly, and less than or equal to 0 means that the left-hand side has to be negative semi-definite. And, you know, this is pretty much a case where you have Gx and psi less than or equal to 0, where G is convex in X for any given psi. So an LMI gives a function G, and this is a convex constraint in X. However, in my own community of control people, this kind of constraints were not treated stochastically, but in a fully deterministic manner. So we were insisting that the LMI had to be satisfied for each and every value outside. There is no probability. And I should mention that this is very popular in control, because if you take a Lyapunov of stability, for example, it boils down to an LMI. If we take H2 control problems, again, we have this kind of constraints. So the fact that it is for an xi comes with the good news, because for one given xi, the feasibility domain of the constraint is convex, and the intersection of convex is convex. So we call this a robust approach for an xi, and the intersection of convex is convex. The feasibility domain is a convex set. And the people were looking into problems of this type, minimizing some cost CX, reflecting control specifications, under LMI constraints to be satisfied for an xi. Now, the point is that as long as CX is convex itself, this is a fully convex problem. But this didn't mean that this problem was easy to solve. And the reason was that this is what we call a semi-infinite problem. Because normally the number of optimization variables is finite. Say, X belongs to a finite dimensional vector space. But despite this, the second row refers to infinitely many constraints, because psi is normally ranging an infinite set. So semi-infinite, finite in the number of optimization variables, but infinitely many constraints. And this problem is tough, very tough to solve. Probably it's often NP hard. So let me focus a bit more on this. So up there, you see again the LMI constraints. So there is a domain for psi, and any psi maps into a domain for the matrices up there, which can take any shape. Now, there is a special case where the problem goes back to fully finite, and this is the one. So if the domain in the space of matrices turns out to be a polytope, then by a one-line proof, you show a vertexization argument that claims, okay, if you just enforce satisfaction of the LMI constraints for the vertices, this automatically implies satisfaction for all other points inside. So in that way, you can go back from a semi-infinite problem into a fully finite, because finitely many optimization variables and then finitely many constraints. Point was that very often the domain was not naturally a polytope, and it was common practice in those times to then envelope the real uncertainty domain for the matrices into a polytope. And then, again, only the vertices were enforced. And it's pretty obvious how the story goes. So from the vertices, you get satisfaction of all the constraints in the polytope, and thereby of all the initial constraints, because the polytope is enveloping the original set. The drawback, and it was a major drawback, was that this is conservative. And the reason is that, especially in a high-dimensional space, the additional room you have to add to come up with the polytope is massive. So in other words, if you optimize based on this polytopic enveloping, then the final result is worse. At times, it was much worse than the actual optimal value. So I remember that around the year 2003, 2004, I was looking to these problems everywhere. Many control problems, optimal control, and I told myself, can we instead make a stochastic relaxation? So can we deviate from enforcing that the constraints are satisfied for each and every value of psi, and come up with a new scheme where on the one hand you have solvability, that is a convex problem, but also on the other hand we can keep control on the type of approximation we are making. And the idea was very easy. So the idea was, let's sample from the domain for psi. This maps into samples in the domain of the matrices. And then we just enforce satisfaction of the constraints for the maroon dots. So pretty much instead of being an outer approximation, which was conservative, this is an inner approximation. And that's a different way to go back from infinitely many constraints into finitely many. So easy to solve. This was the introduction of the so-called scenario program. So minimize CX, subject to finitely many constraints drawn from the domain of psi. Some remarks here. That's tractable because that's convex, finite. And it's super optimal. Super optimal must be explained. Super optimal with respect to what people in my community were doing, because they were doing fully robust, and the scenario program is less constrained than the original one. So super optimal means super optimal with respect to fully robust. But then, of course, the question was, well, what kind of solution is this? Because, I have infinitely many constraints. I just sample. And what happens to all the others, those that I have not seen? So this is a tough part that we had to investigate. And put in a more formal way, this can be formally stated is the solution chance constraint feasible. So let me focus a bit more on the type of problem we are looking at here, just for everyone to understand the details. So up there we have again the scenario program. Then let me introduce the notion of risk. That's very straightforward. The risk for a point X is the probability that an xi is in violation of the constraint. So in other words, for an X to be chance constraint feasible, the risk must be less than alpha. Low risk, less than alpha. There is a point here that I should mention explicitly. The blue program is itself a stochastic program, because I draw a sample of C sub I, and I have a blue program, scenario program, which will have a solution and a risk. But if my sample of draws is a different one, I have a different problem and a different risk. So the blue program is not deterministic, it's stochastic in itself because of this randomization. That is, the C sub I have been randomly sampled. Therefore, as I plug the solution X star to the blue problem into my risk function, this is random. Is a random variable, is not a number. So what we are after here is really studying the distribution of a random variable. In the year 2008, with Simone Garatti is one of my best friends and the co-author of all the fundamental results in this field. We proved this result here. So it says that indeed the risk of X star is less than or equal to alpha. So the solution to the scenario program is chance constraint feasible at level alpha with a probability. The external probability refers to the sample I have drawn, which is bigger than or equal to a certain expression, which is a beta distribution, which depends on D. D is the number of optimization variables, and N, which is the size of the sample. this result holds true totally distribution free. So the initial distribution that generates the psi is immaterial for the validity of the result. And on top of that, the inequality becomes an equality for a full class of problems, the so-called fully supported problems. So in other words, no one will ever be able to step into this room in the future and say, I have a better result than this, because the result is tight for a full class of problems. But let me explain how you can move from this, because it's getting a bit complicated, because you have the chance constraint level, risk extra less than or equal to alpha, but then you have an external probability given by the randomization procedure. So let me explain how you can move from this into the chance constraint feasibility. To start with, the next slide shows typical beta distributions. So start from the one in the middle, the red one. So this is the beta distribution when n, the number of draws is 200, and the d is 30. So a optimization with the 30 optimization variables. The blue is when you increase the number of optimization variables. It shifts to the right. So the interpretation is that if you use randomization, the scenario program, you get a higher chance to have a larger risk as the number of optimization variables increase. Now, if you double n from 200 to 400, you shift back to the left. So let's pick just one case. So the story goes that you can cut the distribution, the density in this case, at alpha, and everything which is on the left is chance constraint feasible. And then you are left with the tail. Importantly, this tail can be pushed down to be very small. So the risk of X star is less than or equal to alpha with a high confidence 1 minus beta, and easily enough, the tail can be pushed down to 10 to the minus 6, 10 to the minus 8, because a beta distribution is very thin-tailed. So you do not have to sample too many draws to get that the result is. And so with the practical certainty, this is not mathematics, because there is still 10 to the minus 6. But with you can make 10 to the minus 10 if you want. But with the practical certainty, you come to have a feasible chance constraint solution. So randomization provides a way to find chance constraint feasible solutions independently of the distribution of uncertainty. And this is very important because initially you have a certain distribution, you go into randomization, now you have a finite mean, so you forget about the initial distribution. But then it is the theoretical framework that takes care to bridge the final result with the initial distribution, whatever the initial distribution was. But the story goes on here, and around the year 2008, 2009, we were arguing the following way. So the scenario solution has a better value than the robust solution. That's obvious. However, and this was really the time when we start looking to the community of most people here, stochastic optimization and the people in this business, because in chance constraint optimization, accepting risk alpha results in a better performance. And that actually is the reason why you want to strike a happy compromise between risk and performance. And the question, of course, was, can we incorporate this concept into our randomization framework? So the idea here is very simple. And I'm going to explain it with a two-dimensional example. X1, X2 are the two components of the optimization vector, and say that we optimize downward. And each line corresponds to a draw, or how we call it, a scenario, Xc1, Xc2, Xc3. So we had to stay above. So if we solve the previous a scenario program with all the constraints, then we arrive at the black solution, which is the optimal feasible solution. And then the idea, of course, is to remove one after another various constraints. I hasten to say that this is pretty much an empirical or randomized chance constrained optimization program. So if I come to you and say, okay, here there are 500 constraints, you can remove 10 of those. Again, the feasibility domain becomes highly non-convex. However, there is a handle here, and the handle is that we are looking into finitely many constraints. And this gives us a very helpful hand, as I will show in the next slide. This was really the time when we contacted Professor Prékopa, because so this was the end of year 2009. So I and Simone were, spending hours and hours every day on this topic, but we were coming from a different community. So we were asking ourselves whether this was meaningful for people in the stochastic optimization community. So we contacted him, and our correspondence went on the whole first part of 2010 as well. And I had to say that Professor Prékopa has been so much supportive to us, and this really gave the extra buzz for us to continue this research. Pointing out the relevance of this as an alternative. And actually, I had to say that at the point, Professor Prékopa even came to be familiar to us, telling us of anecdotes dating back to the old days, the 70s, when he started working on this topic and developing his fantastic theoretical framework. He told us of the three Americans, Charles Cooper and Simons, and he had contact with them, and two of them flew into Budapest to meet with him, because, chance constraint had been introduced just as an idea by these people. But Professor Prékopa was really the pioneer in this field who set up the whole fantastic mathematical framework. And so, to us, this was really a time of extra exploration into different community, and this was very important for us, not just as scientists, but to come to understand, to be part of a different story. So in the year 2011, we then published the following result. So if you dig into the infeasible domain, so you remove one constraint, you remove another one, you go down, then extra k is the solution after you have removed k constraint. And we were able to prove that the risk is less than or equal to alpha, so it's chance constraint feasible at level alpha with the probability which is given by the expression on the right-hand side, and this is just an extension of the previous result, because if k is 0, no removal, then the binomial in front of the summation is 1, and the summation, so you get back to the beta result. So this result holds for gxi convex in X, but apart from that, any dependence on xi and any distribution of xi. So there is no conditions on log concavity, whatever, so you get this. But then you say, okay, but then you have still an empirical finite many, but you have to find the solution in a domain which is non-convex. This is not true. The reason is that this result holds for any discarding algorithm. So in other words, it is not required that you find the optimal solution, which can be a formidable task. So you can remove in whatever manner you want. So what we do most of the time is we take the solution and we look for active constraints to be removed. So we try this, we try that, and we remove the one that gives the largest immediate improvement, and you keep going. Of course, there is no proof that you end up with the optimal solution. If you can do that, please do. That's even better. But the theorem holds true rigorously, no matter what kind of removal algorithm you use. So perhaps use a greedy scheme. The value can be inspected because you sample, you have the program sitting in your computer, and you see the value. The value is something that is visible, is a statistic of the data. But the theorem provides chance-constrained feasibility results. So when you move to that level, the bridge again with the initial distribution is taken care by the theoretical approach. So my message is, as long as there is a problem that you can solve with traditional methods, so the domain is feasible and the feasibility is convex, this gives an alternative. When the problem is not solvable, this shows that you can go through randomization, you can remove according to your best approach, you inspect the value, that's in your hands to see whether or not it is palatable, acceptable for you, but you get very strong, precise guarantees in terms of feasibility. Oops, sorry. Okay. I would like just to finish in the remaining 3 minutes with an example. This is a famous example in my community, which is the community of control. So this is the lateral motion of an aircraft. This was introduced in the 60s by Taylor and Cotters, and resumed by many others, John Moore, Anderson, Brian Anderson, Boris Polyak, Roberto Tempo, many others. But so there is an aircraft. The lateral motion of the aircraft is governed by an ordinary differential equation with the linear with the 4 state variables and 2 inputs. So the 4 state variables are the bank angle, that's the aircraft bank angle, the derivative of the bank angle, the side slip angle, which is the angle between the longitudinal direction and the direction of relative wind, and the yaw angle. And the 2 inputs are the displacement of the ailerons, which are, the movable elements on the wings, and the displacement of the rudder on the tail. This problem comes traditionally with 7 uncertain parameters that are within a range, an interval. So altogether, you have a 7-dimensional hyperrectangle. And the goal is to minimize a quadratic cost. So this is effectively an LQ control problem, which, by the way, can be written in the standard form I showed before. You minimize a cost Cx subject to LMI constraints. So this requires a lot of rewriting, short complements, but in the end, that's a rigorous reformulation. So in my community, this problem was attacked by saying, okay, I would like to have for any xi. And by the way, this problem is easy to solve because to start with, you have a polytope because it's a hyperrectangle. So I solved this for you, and the result was 16.8, which is too large a value to be acceptable for this type of problem. So I have to say that in my community there is a bad habit, which is when the value is too large, there is an attempt to resize the uncertainty. So you push your luck. You say, okay, perhaps I was asking for too much. Let's resize the hyperrectangle. This is I've seen this many times, and in this case, I I took uniform probability in the hyperrectangle, so probability is volume. And this is the gentle improvement you get in the cost value as you resize. And people in the stochastic optimization community knows very well that resizing is kind of nonsense because quite likely the portion of uncertainty that are going to have the largest impact on the cost is not the ultra shell. So you had to look for relevant parts. So we applied the algorithm that I showed you before here. We sampled 2,000 points. And then we used a fully greedy approach. So 2,000 points, the optimization domain, looking at for active constraints, and this was the solution. So as you remove constraints in the randomized framework, the solution finds its way to remove suitable portions of in the uncertainty domain. The point is that the value can be inspected because this is sitting in your computer. The invisible part is the alpha, the probability of violation of the constraints. And in the abscissa, you see the upper bound to this probability as given by the previous theorem. So you come to have the full picture cost as you go down versus upper bounded to the probability of violation, and you can choose, in this case, my selection was 0.05 probability, which is good for me, while the value had dropped by a factor 2 or so. Okay.